Good evening all. Let's get started with this week's session. So this week is a pretty straightforward problems. All of them are related to second law thermodynamics, Carnot efficiency, and refrigerator and heat engine problems. So this shouldn't be much of a problem. So we'll conclude the session as possible. We have the first problem here. You have a heat engine. Let me just hide the solutions. Yes. So the first problem is the heat engine receives the heat at a certain rate of 1500 kJ per minute and gives an output of 8.2 kW. Determine the thermal efficiency and the rate of heat rejection. So how do you define thermal efficiency? Is basically your output by input. The output in case of heat engine is the work done, and input is the heat that you are supplying from the source. So thermal efficiency is the work output divided by the heat rate. So all you have to do is ensure the units are correct and then determine the efficiency. The second question asks you the rate of heat rejection, the heat rejection. So this you can obtain from obtaining by doing energy balance. So or basically, if you apply the first of thermodynamics. Oh, sorry, I think my screen is not being shared. I think now it is visible. Yeah. So how do you determine the heat? So you apply the energy balance, which gives you that this is the heat supplied, this is the work done by the system. So it is a cyclic process. So whenever you say heat engine, it means it is a cyclic process. So in a cyclic process, delta U is 0. So the net heat addition should be equal to the net work done by the system. So the net heat addition is this minus whatever is the heat rejected, and that equals the net work output. So from there, it should be directly calculated. So efficiency is output input. So again, just to give you two concepts, so you have a heat engine, and you also have a refrigerator. So in a heat engine, you take heat from the source and then you reject heat to the ambient by doing some work on this ambient. In case of refrigerator, you take heat from the food, reject heat to the ambient, and you also take work from the compressor. So here efficiency is your output, that is W, divided by your input is Q. In case of refrigerator, if you want to define the efficiency in loose terms, is basically your whatever is your output. The desired output is to reject certain amount of heat from the food, so that is Q2 divided by the work that you are putting in, that is W. So that is how we define for a refrigerator. So since that this value is usually not less than 1, so you basically call it COP. You give a new name for it, called the coefficient of performance. So we'll look at it in the next problem. So eta is calculated directly. So you know W, you know Q1, so you can calculate eta from it directly. And then when you apply the energy balance, that is Q1 is W plus Q2. Since W and Q1 are known, Q2 is Q1 minus W, which gives you a value directly. So since it is a straightforward problem, not spending too much time on discussion. If you have any queries, please post it on the chat, then we can discuss. Second problem is during a certain process, you have a system that receives 30 kJ of heat from a reservoir and does 60 kJ of work. Is it possible to reach the initial state by an adiabatic process? So come back. So what is meant by a process? A process is basically a path that you take from state 1 to a state 2. So from state 1 to state 2, to move from state 1 to state 2, the particular process receives 30 kJ of heat and it does 60 kJ of work. So now I want to bring back the system to the same initial state using an adiabatic process. So is it possible or not? So in the sense, what do we do? So we apply the first law of thermodynamics to see whether energy balance is happening. So even before that, so what do you mean by reservoir? Is the reservoir is anything that has an infinite heat capacity, which means that by taking or adding heat to the reservoir, you are not changing its temperature anyways. So from state 1 to state 2, Q is specified, W is specified, so you can calculate delta U from the first law, which gives you around minus 30. So since delta U is the state function, it only depends on the initial and final states. If you want to move from state 2 to state 1, your delta U should also be exactly opposite. So that will be 30 kilojoule. And you know that it is an adiabatic process of U is 0, so which means W is minus 30, which means in order to complete this cycle, you need to supply 30 kilojoule of food in 30 kilojoule of heat in the reverse adiabatic process. Only then you will be able to reach the original state. Are there any questions? That is there are no questions. So we move to the next problem. So here we are asking to find the coefficient of performance and the heat transfer rate in the condenser of the refrigerator, which has a refrigeration capacity so and so and a power input of so and so. So just as we discussed before, your coefficient of performance or efficiency is basically output by input. The output that I want from the refrigerator is the refrigeration capacity. I need to meet this refrigeration capacity. So this is the output divided by input is the compressor power that I am supplying. That is 0.75 kilowatt. So that will give me the COP directly. In the condenser, so if you see the refrigeration cycle, so you have a compressor. So this is the cycle. So this is straightforward. So the COP is defined in this way. Just ensure that numerator and denominator are on the same units, and then we get the COP directly. Now, if you see this process, so it's a little cumbersome. So let's remove these two. So you have a cycle here. So the compressor does some work on the refrigerant, and then it gets into the condenser where it ejects heat to the ambient. From there, it goes to some throttling valve where it converts from the gaseous phase into two-phase basically, or you can, for now we can say that it converts into a liquid phase, and the liquid goes into the evaporator where the evaporator is in contact with your refrigerated space. So it takes heat from your refrigerated space and evaporates. So basically it's a phase change from liquid to vapor phase, and then the vapor again goes into the compressor, and this cycle keeps on repeating. So the question now asks you to find the heat rejection at the condenser. So you are supplying work at the compressor, the evaporator is taking heat, and condenser is rejecting heat to the ambient. So W plus the Q2 is the evaporator equals to Q1 is the condenser one. So 10 by 3 is the condenser one that is being rejected from that is from the food. It is given as the refrigeration capacity plus 0.75 is the work you're doing on the compressor. If you add both of them, you should get the heat that is being rejected from the condenser. Are there any questions? Yeah, I guess it is clear. So the next problem is also very similar. So if you see the trend in all these problems goes in the same way. So you basically have so up until now we just had one equation. So and that is just the energy balance. So delta Q equal to delta U plus delta W. We just have one equation, but now we have one more additional equation that we are looking up here. So that is something that we will see in this problem. So up until now we just have this one equation, that is energy balance equation. Now we have one more additional equation that is coming from the Carnot's equation, that is Q1 by T1 is Q2 by T2. This is valid only for reversible processes. So we are assuming that this is a reversible process. So now we have two equations. So and basically you have five variables here. So two equations and five variables. So most of these questions will give you three of these parameters, and you'll be asked to find the remaining two. So this is a very straightforward exercise. So it's just solving a set of equations. So you'll be given out of the five variables, three variables will be given in some way, directly or indirectly, and you'll be asked to find the remaining two variables using these two equations. So in this, all you need to know is what is Q1, what is Q2, what is W, and what is T1 and T2. So here, let's say T2 is so let's say T1 is a higher temperature, that is 35 Celsius, and T2 is a lower temperature, minus 12 Celsius. Now Q2 is the heat that is being taken from the freezer. So the freezer, there is a leak into the freezer. I have to remove this heat from the freezer, otherwise the freezer temperature will increase. So this is basically Q2. Why am Q2? Because you are taking heat from T2, I'm calling it Q2. So from energy balance, we know Q1 is the heat that is being rejected to the ambient equals Q2 plus W, and from the Carnot equation we have Q1 by T1 is Q2 by T2. So the work done is equals Q1 minus Q2 from this relation, and if you use Q1 as, if you just take this T1 to this side, that will be Q2 T1 by T2. If I just take T2 outside, I have this equation. So if you just substitute the values, you calculate the W. So the question specifically tells you to find the least power necessary to pump this heat out compressor. So why are we saying that this is the least power? This comes from the relation that we have here. So this relation is valid only in case of reversible processes. So if a certain process is irreversible, which means there are some irreversibilities like heat transfer happening at a finite temperature difference and some other cases. So what would happen if there is an irreversible process? It would increase the efficiency. So which means in this case, you would have, instead of supplying 0.3 kilowatt, you would be supplying a higher amount of work. Or to those of you who are more mathematical, COP is defined in this way. So COP will be maximum whenever you have a reversible process. So any irreversibilities inside your cycle will reduce the value of COP. So if COP is reduced, your W will increase. So this is the maximum possible COP for a given refrigeration load. So here the refrigeration rate is fixed. For this refrigeration capacity, this is the maximum COP. So the W will be the minimum W. So if this value decreases, then W will increase. So that is why this is the minimum power that is required. Is this clear? Are there any questions? Yeah, feel free to type it in the chat box if you have any queries. I guess there are no queries, so we'll move on to the next problem. The house requires a certain amount of energy for heating in winter. Heat pump is used to absorb heat from the cold air outside in winter and send heat to the house. Work required to operate the heat pump is 3 into 10 to the power 4 kilojoule per hour. Determine the heat absorbed from the outside, coefficient of performance. So again, this is also straightforward. So you are taking heat from the ambient, and the heat pump is taking heat from the ambient, and it is taking work from the compressor, and then it is heating up your house. So Q2 is basically the heat that is being sent into the house, and that is given as 2 into 10 to the power 5. And work done is also given. So if you apply the first law, whatever in is equal to the out. So Q1 plus W should be equal to Q2. So Q2 is known, W is known, you are asked to find Q1. So you can calculate Q1. And then COP, again, just as you said before, it's your output by input. My objective is to have a certain value of heat that is being supplied to the house. So this is my output. And my input is the work that I am doing on the compressor. So that is W. So Q2 by W will be my COP. Now instead, if you are using the same thing to cool your room in case of summer, so what would happen is you are taking heat from your house. So this arrow will get reversed and this arrow will get reversed. So again, my output will be this one and my input will be this one. The only thing that will change in case of your equation is the temperatures here and here will get interchanged. But other than that, like outside temperature will be higher and inside temperature will be lower. That's the only difference that you'll be having in summer. Are there any questions? Just to be clear, all you need to do in case of this efficiency or COP calculation is basically remember the formula that output by input, where output is basically what is my objective and input is what is effort that I am keeping in to meet that objective. That should make things clear. In case of heat engine, my output is the work done by the system and my input is, in order to do that work, I am burning some fuel, or in case of a steam, you are burning some water, some fuel to heat your water to make steam. So whatever is my input is basically the heat that I am supplying to boil the water. And work is basically whatever is the net kinetic energy that I'm getting out of your steam engine. Or in case of an IC engine, or if you consider a battery, sorry, battery wouldn't be an appropriate one, but then the energy would be supplied from whatever chemical reactions that are happening. So that stored chemical energy that is getting converted is basically your input, and the output is the net voltage times current, that is the net output that you are able to take from the terminals. So if you would compare with an IC engine, the petrol or diesel that you're keeping in your car, the chemical energy stored in it times the efficiency of the conversion will give you the heat input, that is your effort. And the output is basically the mileage or whatever range that you are going, that would be your output. So basically the work done is that output, and input is your fuel energy. In case of a refrigerator, the output is to cool a particular refrigerated space. So that is your Q2, and then the work done on the compressor. So that is the electricity that you are providing to the compressor. So that Q by W will give you the COP in case of refrigerator. So its bottom line is output or objective divided by input or the effort. I think that clears up the question even in the discussion forum. So we'll move on to the next problem. So again, just as I said, so what is the highest possible theoretical efficiency? Whenever we say the highest possible theoretical efficiency of a heat engine or the highest possible COP for a reverse Carnot cycle is of reverse cycle is basically optimum when you have a Carnot efficiency. So if you have these two temperatures, so all you need to do is use the relation T1 and T2 are given, so eta is W by Q1, and then you have one more relation as this, the first law, and this is from the Carnot equation. So eta maximum is this one. But if you see the typical thermal power plants operated much lower than this. So they operate around 30% or 40% efficiency. So even though our theoretical efficiency is much higher, we are not able to reach it. So why is it that happening? It's because of irreversibilities. So one of those irreversibilities is the heat transfer happening at a finite temperature difference. So for example, if you want a certain amount of heat, so let's say 30 watt of heat to transfer from this, so if you see here, the furnace gases are at 2100 Celsius. And then you have your working fluid, that is your steam or your water, whatever is your working fluid, that steam has to take heat from this 2100 Celsius gases. How does it take heat? In order to take the heat, the water should have a temperature lower than 2100. But how much lower? usually the heat transfer rate will be much higher if the temperature difference is higher. If as you decrease the temperature difference, the heat transfer rate will decrease. In order to ensure the same amount of heat energy is transferred, you need to wait for some very long time so that you will have the same amount of heat transfer. But then that would mean you are having a very slow cycles. That would mean you are having a power plant which is generating power very slowly, which is not practical. So here comes the trade-off. So if you want to have a higher theoretical efficiencies like Carnot cycle, you need to be operating very slowly, which will not meet your requirements. And then in order to, if you want to speed it up a little, then you are doing it at a much lesser efficient processes. So this is where the trade-off comes. The speed between the efficiency. If you want a higher speeds, then your efficiency drops. And if you are at lower speeds, your efficiency increases, but then that is not useful to us at any point of time. So the next problem, some problem. So again, you have a Carnot cycle that is operating between a source and sink temperatures of 250 Celsius and minus 15 Celsius. If the system receives 90 kJ from the source, find the efficiency of the system, net work transfer, and heat ejected to the sink. So this is again, as we said before, you have 5 parameters, Q1, Q2, T1, T2, and W. And then you have two equations. One is the first law, that is Q1 equal to W plus Q2. And then you have, from the Carnot equation, you have Q1 by T1 is Q2 by T2. So with these things in question, so you can have at most two unknowns. So that is the unknowns that you are having. So you have T1, T2, you can directly calculate efficiency from there. Q1 is given. So once you know the efficiency in Q1, you can calculate W from it. W is eta times Q1. And then you use the first law. Q1 is Q2 plus W. So you can calculate Q2. Q2 is the heat ejected to this thing as Q1 minus W, the supplied minus work done by the system. So these are again straightforward. I don't think there are any questions in this. So we'll move on to the next problem. So inventor claims that his engine has the following specifications. So he says that his engine operates between the temperature of 750 Celsius and 25 Celsius, and the power developed by the engine is 75 kilowatt. And he also says that his engine burns 39 kilogram per hour of fuel, and the heating value is less, assuming that this is the maximum amount of heat that is being generated without any incumbents things. And then what would happen is, how do you know that these values that he is claiming is valid or not? The idea here is the efficiency of any real heat engine is less than Carnot efficiency. So with these values, you calculate the Carnot efficiency, you calculate the efficiency of his heat engine, and if his heat engine efficiency is less than the Carnot, then it is not valid. So how do you do that? So I know Q1. Q1 is basically the heat that is being supplied from the source. So that is 3.9 kilogram per hour of fuel times this. So if you multiply the heating value times the mass of the fuel, that will give you the total heat supplied from the source per hour. And if you just convert it into kilojoule per second, you just divide by 3600, so you get value in kilojoule per second. And he claims that the work done is 75 kilowatt. So from there you can calculate the efficiency as 0.929. And since temperatures are given, if you would operate a reversible Carnot cycle, then the efficiency is 70%. So the Carnot efficiency, the real efficiency can never be higher than the Carnot efficiency, so the claim is not valid. Now, if you were to say the same in case of refrigerator, you would, instead of calculating efficiency, you would calculate the coefficient of performance and see if the COP should actually be much higher. If you see the equation for COP is basically the output by input, and Carnot is where you have the minimum amount of work done. So COP will be maximum in case of a Carnot one. So the actual COP versus the Carnot COP. If the actual COP is greater than Carnot COP, then the claim is not valid. I think this is clear. There are no questions, so we'll move to the next problem. A cyclic heat engine operates between, again, this is again a standard problem. So it operates between two temperatures of two set temperatures, so you can calculate the efficiency. And from there, you need to calculate the heat ejection rate per kilowatt net output of the engine. The work done can be taken as 1 kilowatt, and with these, you can calculate efficiency. So it is again a straightforward standard pattern that keeps following. You have T1 and T2. The work done you can take as 1 kilowatt. With this, you calculate the efficiency first, and Q1 is defined as W by eta. So from there, you get the heat from the source. Once you have the source heat, the reject sink heat can be calculated as the source minus work done. So that gives you a value of 0.5 kilojoule per second. And why is this called the minimum? Because again, just as we said, eta will be maximum in case of Carnot cycle. So if eta is maximum, Q1 will be the minimum. So if Q1 is minimum, you see Q2, Q1 are directly related, so Q2 will be minimum. So for suppose if you're operating at if there are any reversibilities, then this eta will decrease. So eta will decrease, so Q1 will increase and Q2 will increase. So you can see that if so, the maximum possible efficiency will give you the minimum value of Q1, which will give you the minimum value of rejection. For all of this is assuming that your work done is constant and only your eta is changing in some way. If your work is also changing, then it becomes like you cannot standardize these things. Move on to the last problem. A fish freezing plant requires 40 tons of refrigeration and the freezing temperature is minus 35 Celsius while ambient temperature is 30 Celsius. If the performance of the plant is 20% of theoretical reverse Carnot cycle, working within the same temperature limits, calculate the power required. Unlike all the previous problems here, we are not saying that it follows the Carnot reversible cycle, but then you can use the Carnot equation and then do something else to relate between what is happening in the real time. So for example, in this problem, you have T1 is the ambient temperature at 303 Kelvin and T2 is your freezer temperature. You are taking heat from the freezing plant. So T2 is the temperature of the freezing plant. So Q2 will be the heat ejected from the freezing plant, that is 140 kilojoules per second. If the refrigerator is considered as system, so this is the heat that is being taken into the system. So this is the Q2. And then Q1 is the heat that is rejected out of the system. So that minus Q1 is equal to W. This is from the first law. And then we use the Carnot equation. Q1 by T1 is Q2 by T2. So using these two relations, you can directly calculate Q1. Q1 is Q2 times T1 by T2. That is 140 times 313 by 238. That will give you a value of Q1 and so on. So now what we do is this equation is valid only in case of a Carnot cycle. So for the Carnot case, so if this equation is valid, this is the Q1. So for Carnot case, W is calculated as 140 minus this one. So that is giving a negative value because this is work done on the compressor. So it is expected to be negative. Now, as we said before, if the performance of the plant is 20% of the theoretical reverse Carnot cycle working within the same temperature limit. So if your performance is reduced, which means you have to do more work. Since it is a refrigerator, the work done for actual compressor will be higher than the work done for Carnot, and it says 20%, so this will be 1.2 times the Carnot. If it were a heat engine, then the work done by the heat engine will be 20% lower, so that will be 0.8 times the Carnot work done. I think this is clear. So in case of refrigerator, you have to do more work, so this will be 1.2 times this, or in case of a heat engine, it will be lesser, so it will be 0.8 times work done. So this will give you a net value of 45.88. If you're not convinced this one, you can also write the equation directly. So even from there, you will get the same answer. Hope there are no questions. This week the problems are pretty straightforward, so I wouldn't like to spend more time on this. If you have any queries, I'm open for discussion. So bottom line, we just have to remember two equations. One is the first law that we have, the net heat input equal to the work done by the system plus the net heat output, and this Carnot equation that we have. So we have 5 variables in total, Q1, Q2, W, T1 and T2. And then you have two equations, so at max they can ask you to solve for two unknowns. So the remaining three quantities will be specified either directly or indirectly. Yeah, I guess there are no questions, so I think we are good to end the session today. Thank you for joining. We'll meet next week at the same time.